In this video, we're going to take a look at gases, the mixtures of gases, and how gases move. And we're going to do that with respect to Dalton's law and Graham's law. Dalton's law takes a look at a mixture of gases and how that mixture of gases contributes to the overall pressure. Every gas within a mixture of gas has what we call a partial pressure, how much pressure that gas contributes to the overall pressure of a mixture of gases. In that mixture of gases, you can find the total pressure of the mixture of gases by adding up the sum of all those partials. We know that particle and moles have a relationship to the overall pressure in a direct relation. So as we look at the different mixtures of gases, the amount of particles that are there will affect the pressure the same amount. So the total pressure ends up being the sum of all of those partial pressures. In this case, P1 plus P2 plus P3. And if there's more gases, you can just keep adding in more and more gases to it, then add together to make that total. So we see that here with these three different gases, A, B, and C. In container A, we have 4 of those green monatomic gas particles contributing to 100 kPa of pressure. And then in B, we have those 10 red monatomic gas particles contributing 250 kilopascals of pressure. And then in container C, we have 8 diatomic of those blue molecules contributing to 200 kPa of pressure. And when I put them all together, I total them all up in container T, and I still have those 4 green atoms and those 10 red atoms and those 8 blue molecules. And when they come together, they have a total pressure of 550 kilopascals, or the 100 plus the 250 plus the 200, which we saw when they were separated into containers A, B, and C. I could also rework that formula, and if I knew the total pressure was 550, I knew that gas A contributed 100 kilopascals of pressure and gas B contributed 250 kilopascals of pressure. I could determine what pressure must be coming from C by taking the total and subtracting those two partials from it. Graham's law takes a look at how gases move. Gases move through diffusion. When they're in an open area, those gases will move from areas of high concentration to areas of low concentration. Just like what happened in the cells of your body, when there's a greater concentration of a substance outside of your cells than inside your cells, then through osmosis, water brings those molecules into your cells to then get an equal concentration inside and out. Same thing happens with gases. When somebody in the room near you is having an orange and they peel an orange, and those orange-smelling molecules are released into the air, they will diffuse their way to you until then you smell it a couple of minutes later. And eventually those orange-smelling molecules continue to diffuse, and eventually you don't even notice the orange smell anymore because it's so spread out throughout the room and the building of which you're in. Gases also effuse. They work their way through these tiny little itty-bitty holes through the container which they are contained in. You notice this when you get a balloon, and that balloon is floating up in the ceiling because it's filled up with helium, but then a couple days later that balloon is on the floor. Because those small helium atoms, 2 protons, 2 neutrons, 2 electrons, mass of only 4, are really, really small, and they can find their way between the molecules of the balloon that are holding them in. And so we end up with a rate that is equal to the ratio of their molar masses. The square root of that, of those that have a lower molar mass, will diffuse and effuse faster than those of a higher molar mass. And again, it's inversely proportional because of the way that the kinetic energy of these particles is calculated, which we'll see in this next slide. So we can get a relative rate of those two different gases, rate A versus rate B, by again taking the inverse of their molar masses and then the square root of it. So this works best when you take the lower molar mass as A, that way you get a number greater than 1, rather than if the molar mass of B was greater and you use that as A, and you get a ratio that would be less than 1. But for any temperature, that ratio will remain constant because they will increase at the same rate. We notice that because kinetic energy, the energy due to a particle's movement, is equal to 1/2 their mass times their velocity squared. So 2 gases in the same room would have the same temperature, therefore they have the same average kinetic energy. So if you set those two equal to each other and then move the mass to one side and the velocity to the other and set those equal to each other, you'd end up with rate A versus rate B would be the square root of molar mass B over molar mass A, and therefore that's where that square root of their masses gives you the ratio of their rates. So take a look at nitrogen versus helium. How much faster is helium going to diffuse relative to nitrogen? So again, we need the molar masses for these to then get the rate, the ratio of those rates, of the helium to the nitrogen. And it works again best if you use the lighter one as A. So rate of helium versus the rate of nitrogen, because helium is going to move faster since its molar mass is 4. Nitrogen, being diatomic, has a molar mass of 28. So rate of helium is equal to the square root of the molar mass of nitrogen over the molar mass of helium. And then we plug in the 28 grams for the nitrogen and the 4 grams for the helium. 28 divided by 4, square root of 7. Therefore, we end up with 2.7 times faster that helium is going to move relative to nitrogen. Again, at low temperatures and at high temperatures, they're going to change at the same rate, and there's always going to be 2.7 times faster for the helium than for the nitrogen, no matter what the temperature is.